Alright guys, welcome back to Med Talk. My name is Katalina, and as you guys can clearly see, I have my amazing counterpart Gabriel missing here. He is in the back right now studying for his anatomy exam tomorrow.
Yay.
But tomorrow I am taking my chemistry exam, so I'm going to go ahead and explain some more chemistry to you guys in this awesome series that we're talking about the atom's structure. So this is episode number 3. So if you haven't watched the first and the second one where we talk about atomic structure, the history of it, and mass spectrometry, go ahead and check those out for a little bit of context of what we're talking about today. So we're going to be talking about light waves and photons. So I have a lot of formulas written up here on the board that we'll be using later. And some of them may look familiar, some of them may look like total gibberish, but I will explain all of them, so do not fret. I have got you guys. So we're going to go ahead and start with a little bit of background information. So according to Rutherford's nuclear model, which I talked about in episode 1, electrons move around the nucleus like planets around the sun. And the flaw with the planet-like model is that a moving charged particle would be emitting radiation, therefore slowing down and eventually allowing it to become captured by the nucleus. But emission spectra of substance experiments involved heating gases under low pressure in a tube and observing and recording the visible light emitted. The light type of electromagnetic radiation that exists at a wide range of wavelengths. So this whole capturing thing didn't exist. And instead, we saw visible light coming out of it. So then we can go to the electromagnetic spectrum. And with the electromagnetic spectrum, basically what it is a continuum of electromagnetic waves, and they are arranged according to frequency and wavelength. So wavelength is better to be explained visually. So this is a wavelength, and what we have here, we have our crest is the top part where it peaks up and where it drops down. It's called the trough. And let me see how you spell it because I'm terrible at spelling. Okay, perfect. Now a wavelength is from crest to crest. And a wavelength can also be denoted by the Greek symbol lambda, which is this little funny looking upside down Y almost. So this is a wavelength. It's just from crest to crest. Wavelengths come in different frequencies. So what frequency is the number of waves that pass through a point in 1 second. So wavelength is denoted in the symbol nu, and it is units of 1/seconds, or seconds to the -1st power. And wavelength, I forgot to mention, is typically in meters, but in respect to the electromagnetic spectrum, it can also be in nanometers, just depending on your course and the different numbers that you're given. So I always recommend knowing the conversion factor, that 1 meter is equal to 1 × 10⁹ nanometers. But aside from that, that's pretty much what wavelengths are and waves and all of that. So then we have the electromagnetic spectrum. So I'm going to pop up a picture here of what it looks like. And what the electromagnetic spectrum is pretty much just a bunch of different wavelengths. And so this is measured in meters, this particular one that we have right here. But we have very large waves called radio waves. And those are going to be at a very slow frequency. So they're going to look a little bit like, maybe like this. But guess what? Radio waves are actually what plays in your car when you're listening to the radio. And they come in FM and AM, which is why you have your FM radio and your AM radio. And they are very big. They stretch very, very long and wide. And then we have microwaves. I think everyone should know what a microwave is. It's, not the microwave that you're thinking of. It's just the type of wave that it is, which microwaves emit. And then we have our infrared, and that one is right before we get to our visible light. Visible light is just a teeny tiny little bit of what we can see, even though you see so many colors. It's your Roy G. Biv, and I believe actually that the indigo got removed, just like Pluto got removed. So it's now Roy G. Biv. And so the longest one is going to be red. It's 7 times 10 to the negative 7th meters, and our shortest one is going to be 4 times 10 to the negative 7th. So anytime that you're talking about visible light, if it doesn't end in times 10 to the negative 7 when it's in meters, just know you're doing something wrong. And then we have our ultraviolet. So that's UV radiation, or wavelengths. And if you go look on your weather app, you'll see UV rays. So that is just it's not necessarily the most dangerous one, but it very much so. I think people know it as a cancer-causing ray, and it is because it can get into your body and it's not good for you. Just like if you put your head in a microwave, it wouldn't be very good for you either. And then we have X-rays. So X-rays, think about like when you're going to the doctor, you broke a bone, you have your X-rays. So they actually emit X-rays into you pretty much. And you see the pictures of the bones. So it's just picking up different rays as well. And then we have our gamma rays, and those are the smallest ones because they have the biggest frequency. So they're a little bit more like that, very, very small. And I'd like to remember this spectrum with the acronym Raging Martians invaded Venus using X-ray guns. I don't know, someone in my high school chemistry class said that. It's always kind of just stuck. So I like that one, but you can use whatever acronym you like. So the next thing that we want to talk about is speed of light. So all of these waves travel at the speed of light. Speed and frequency are two different things. So what speed is their speed of light is going to be this factor right here. C is equal to 3 times 10 to the 8th meters per second. And we know that the speed of light, since these are all traveling at the speed of light, is going to be equal to C is equal to nu times lambda, or C, the speed of light is equal to frequency times wavelengths. So with that, we can know that these two are inversely related. What that means is if frequency is increasing, wavelength is decreasing to keep the speed of light the same, and vice versa. So now we can get into particle theory. So particle theory dates back to the 1900s with Planck, and he postulated that the atoms, rather than being able to absorb and re-emit any amount of energy, are limited to a quanta or packets of energy. So he came up with this formula right here. Energy is equal to nu times Planck's constant. And Planck's constant is this number right up here. Some of you might have recognized that right off the bat. It's a pretty famous number. Planck's constant is equal to 6.626 times 10 to the negative 34 joules per second, or joules times second. And so then we can get into the photoelectric effect, which kind of dates back to Einstein. So he's called these packets of light photons, and they can transfer energy to electrons and release them from the metal. In a classical theory, if you shine enough light on any wavelength, you could knock off an electron. However, experimentally, Einstein found that red light, when exposed to red light, no electrons were emitted. And even when you cranked up the intensity of the light, there was still no electrons. Now, when you used a blue light, electrons were emitted. And when you put more intensity, there were more electrons emitted. So then we can go into the 3 laws of spectroscopy from 1859. And that is 1, a hot solid object produces light with a continuous spectrum. 2, a hot gas produces light with spectral lines at discrete wavelengths, which depend on the energy level of the atom in the gas. And 3, a hot solid object surrounded by a cool gas produces light with an almost continuous spectrum, which has gaps at discrete wavelengths depending on the energy levels of the atoms in the gas. So with all this information, this one guy called Niels Bohr came up with the Bohr model. And so pretty much what he said is that electrons move around the nucleus, but in a specific energy level or orbits, that is, energy is quantized. So with this, we found that 1, electrons cannot exist between energy levels. 2, a number of energy levels are available, and the lowest is called the ground state. And let's go ahead and pop up a picture of what that looks like. So our lowest shell of energy can have 2 electrons. Second one can have 8. Third can have 18, and so on and so forth. Electrons can jump to higher orbits, or called excited states, by absorbing certain amounts of quanta of energy. And when electrons jump down from the excited state to ground state, they emit energy in the form of light. So then that gives us this formula right here. So E photon is equal to negative 2.180 times 10 to the negative 18. And I'm gonna go ahead and erase this actually for you guys so I have more space to write all of these fabulous formulas. Now, depending on your class, you may need to memorize some of these. Thankfully, I don't have to memorize these, but just knowing them is handy too. I did memorize them when I was in AP Chemistry, and let me tell you, that was brutal. Final, and then special. And then we also have Rydberg's constant and Rydberg's formula that gives us the inverse wavelength. So we have 1 over lambda is equal to Rydberg's constant, which I'll go ahead and put right here. Rydberg's constant is 1.097 times 10 to the times 10 to the 7th meters, 1 over meters. So we know Rydberg's constant, and then this same thing right here, 1 over n squared minus 1 over n squared final minus initial. There you have it. So now, just so you guys kind of have an idea of, the distance of the electrons and their orbits, imagine the nucleus to be the size of a small golf ball. On the scale, the first electron shell would be about 1 kilometer away from the golf ball, the second shell about 4 kilometers away, the third 9 kilometers away, and so on. So pretty big orbits. The electrons are all the way out there. And so with that, we can go ahead and try some practice problems relating to all of our beautiful formulas right here. Okay guys, so let's go ahead and try out some problems. So the first one that I have is, what is the frequency of the blue emission line at 432 nanometers in the spectrum of the H atom? Now, I'm giving you these formulas, but if you're a professor or teacher, make sure to not look at these formulas when you're solving this problem. I simplified the problem down for you, so lambda is equal to 432 nanometers, find nu. So go ahead and pause it and try it out. So to do this one, the first thing that we're going to want to do is convert nanometers to meters. So we can use this conversion factor right here. And the reason we want to do that is because in this formula we can use later to find frequency, lambda or wavelength is in meters. So in order to do that, we can do 432 nanometers times 1 meter divided by 1 times 10 to the 9th nanometers. So nanometers cancel, and we are left with 4.32 times 10 to the negative 7th meters. And then we can use this formula right here. Since c is constant, it is always going to be 3 times 10 to the 8th meters per second. That is the speed of light, as I have said before. Frequency, or nu is just the symbol, 4.32 times 10 to the negative 7 meters. So what we can do to solve for frequency, again, is just basic algebra, like we've been doing this entire time. You can divide 3 times 10 to the negative 8th by 4.32 times 10 to the negative 7th meters. Meters cancel, you're left with 1 over seconds, and we get that frequency is equal to 6.94 times 10 to the 14th. 1 over second. And that's it. Not much to it, just basic algebra and using your formulas. So let's go ahead and try a different one. Okay guys, so next one is going to be another one using your formulas. I feel like most light and photon problems are using these formulas, so they're not that difficult. So the question says, what is the energy of a photon with a wavelength of 0.0500 nanometers? Given that Planck's constant is 6.626 times 10 to the negative 34 joules times second. So how we want to start this, again, we want to convert our nanometer. So how we want to start this, again, we want to convert our nanometers to meters using that conversion factor we used in the previous problem. So we're going to do 0.0500 nanometers times 1 meter over 1 times 10 to the 9th nanometers. Nanometers are going to cancel, and we're going to be left with 5 times 10 to the negative 11th meters. Okay, so from here we can use this formula because HC and lambda we all know. HC are constants and lambda is right here, our wavelength. So E is going to be in joules, or joules times second. Or no, I'm sorry, just joules. And H is going to be 6.626 times 10 to the negative 34 joules times second. C is going to be 3 times 10 to the 8th meters per second, all over 5 times 10 to the negative 11th meters. So seconds cancel, meters cancel, and we can punch this into our calculator because we're left with joules, which is what we want. And that's going to end up being let's use a calculator. I recommend using a fraction function if you have it, because you don't want to miss any of your numbers when you're punching it in. Also, make sure that you're not missing negative signs. I personally am a very big missing negative signs person. And I think that that is probably one of the biggest silly mistakes you can make. So we are left with 4, well, my answer key rounds up, but I'm going to give you guys the exact number because that's probably what you'll use. 3.9 you know what, this one has 3 significant figures, so we'll do that. 3.98 times 10 to the negative 15 joules. So that's your answer for this one. Again, pretty simple, just using your formulas. So practice, practice, practice makes perfection with these kinds of problems. Okay guys, so this is going to be our next problem. I think that this is the trickiest one. So this is going to be our last one. And it is, what is the ionization energy for an electron in the n=1 orbit of a hydrogen atom? What is the frequency of the light required to cause this ionization? So I simplified it. Ionization energy, frequency to cause ionization. You know that your electron is in the n=1 orbital. So the formula that is the correct one to use It's going to be E photon, because we're trying to find the ionization energy. Not this one, this is going to find the inverse of wavelength, so don't use this one. This would be used for a different kind of problem. So we can start off by saying that negative 2.180 times 10 to the negative 18. Now, n final is going to be infinite because it's not really jumping anywhere right now. So our final is just infinite because we don't know where it's going to. And 1 over 1 squared is our initial. So what we can do to simplify this, make it easier. Well, infinite is going to be 1 over infinity is always equal to 0 because this number is so big and this number is so small in comparison, so it's 0. And then we're left with negative 1 times negative 2.18 times 10 to the negative 18th. And that gives us 2.18 times 10 to the negative 18th joules. So this right here is the first answer that we needed. That is the ionization energy to remove this electron. And the next thing that we want to find is the frequency. So knowing this, our energy, we can use our, which formula is going to be best? I'm going to say that frequency, this one. Let's use this one. Because if not, we'd be going back and forth between here and here and all these different ones. So E is equal to frequency times H. If you want to simplify this for yourself, you can just say E over H is equal to frequency. So I'm going to use this one, but you can use this one and do the math after you've plugged in the values. But we know our energy is 2.18 times 10 to the negative 18 joules. And Planck's constant, which is 6.626 times 10 to the negative 34 joules times second. Joules are going to cancel, so we are left with 1 over seconds, which is the unit of measurement that we want to use. And this is going to end up getting us 3.3 times 10 to the 15th, 1 over second. So this is our frequency. And there you go. There you have it. It's not too difficult, like I said earlier. Just pretty much plugging into the formulas is the biggest thing. Knowing your formulas and knowing how to use them is the biggest thing that you want to do. So that'll be all for this video. Go ahead and check out the next video, and we're going to talk about quantum numbers and all that kind of stuff. So I'll see you next time when we talk med.